a bit off quite a large amount of material here, but I'll try and give you an overview and a summary of what we have been talking about. And what basically inspired me a long time ago was the operator approach driven by Koopman's work. Let me just put a note on the time start. Okay. Really affords great insight into the question of what is quantum mechanics and what is mathematics. And you'll see what I mean as we move on. And the basic challenge originally, and I'm going to talk about work which is quite old, but nonetheless, I think still very relevant, was the question of classical quantum correspondence in chaotic systems. So the issue there was that at the time was that nobody could possibly understand how one could get classical chaotic dynamics for bound systems, but quantum mechanics does not permit chaotic dynamics. And I'll come back to that momentarily. But what I'm going to try and talk about very briefly is this quantum classical correspondence issue. And I have two examples, both of which I'll only be able to discuss briefly, but I'm hoping to direct you sort of to the literature. And that is the so-called quantum no cloning theorem, which I'll show you a classical no cloning theorem, and what I call the classical and quantum Bourne Rule. Let me come to that later. Okay, so it's unusual for me to talk about older developments, but these are older developments. I don't think they're fully appreciated. And in addition to which, I want to pay a bit of tribute to Joshua Wilkie, who did a lot of this work in the past when he was a graduate student with me, and he passed away about 6 months ago. So to me, it's a sad loss to the. Okay, so here it is, old 1996. There was a huge challenge going on, which was that bound state classical mechanics has non-zero entropy, exponential divergence of trajectories, all sorts of characteristics that we attribute to. But you could show that bound state quantum mechanics has a zero K entropy. It shows absolutely no chaos. So what is this qualitative, conceptual problem? You have supposedly a correspondence principle. You start with quantum mechanics and you end up with classical mechanics as, for example, H bar goes to zero. But here we see a situation where quantum mechanics has a characteristic which is no chaos. Classical mechanics has a characteristic of chaos. So it seems to be a real conceptual break between what actually happens in the quantum to classical limit and the idea of correspondence. Now, this is really a serious challenge. It was so serious that people like Joe Ford said that the solution is easy, quantum mechanics is wrong. He said that in print and quite loudly. There are a lot of conceptual directions towards classical quantum correspondence. There's a book by Bukolich on re-examining the quantum classical relationship. It's a very philosophically oriented book, but it does describe at the beginning the chaos problem. Asher Perez is famous for having said, warning, the so-called principle of correspondence, which relates classical quantum mechanics, is elusive and tricky. I'm trying to understand how to get rid of this bottom line, which was discussed before. Okay, so was obscuring the screen for me. So what we're going to focus on in our correspondence discussion are what are called reasonable or classical operators. That is to say, functions of P and Q that are labeled here by bold X. Okay. So one approach did I think is lots of work on classical correspondence where people take trajectories and they, in classical mechanics, and relate them to coherent states in quantum mechanics, but these are conceptually very different entities. What one should be doing, in my opinion, is dealing with the same entity. That is to say, densities in classical mechanics and densities in quantum mechanics. And we developed a formal correspondence program where indeed we used a quantum density matrix and other operators in the Wigner representation, classical density operator and other operators in the phase space representation. with the idea of reliance on quantum mechanics in Hilbert space, classical mechanics in Hilbert space due to Koopman, one could actually be in a place where one could deal with the correspondence properly, given that the entities are the same. Now, there is a lengthy discussion about whether you need decoherence as a mechanism to go to classical mechanics from quantum mechanics, and I'll come back briefly to that issue in a bit. Okay, so what's the approach? The approach is very straightforward. If you look at dynamics in quantum mechanics, it looks like this. The rho dt is equal to minus I L rho, or L is the Liouville operator, the quantum Liouville operator. This has solutions, has eigenvalues. The Liouville operator has eigenvalues rho lambda alpha with eigenvalue lambda. Alpha is going to contain all the degeneracies, and I'm not going to deal with it here in this discussion, but it's certainly dealt with in the papers I will refer to. So this is the eigenvalue problem. And the eigenvalue problem has a solution just like the Schrodinger equation, any other linear operator equation. The time dependence is given by the eigenvalue lambda alpha e to the minus I lambda t. And if we take this into the Wigner representation, it looks like this. The rho Wigner dt is minus I L. L is now the Liouville operator in the Wigner representation, rho Wigner. And here the eigenvalue problem then looks like this on the bottom. But we all know this. What we don't necessarily appreciate, although I'm sure there are people who certainly in the audience who do, is that I can rewrite exactly the same sequence in classical mechanics. That is to say, the rho dt is L classical rho, L classical rho, and L classical is the Poisson bracket with the Hamiltonian. This has eigenvalue solutions, L rho lambda, I call it lambda c, again with degeneracies is lambda c, rho lambda c. This is an eigenvalue solution to this equation. And therefore I can write individual solutions in time evolving as rho lambda c alpha e to the minus I lambda c t. These are, look at that, they look virtually the same. And therefore, if I examine time evolution, then in quantum mechanics, if I start with the Wigner representation rho of x0, then I can expand the solution, the time evolving solution, in a linear combination, a linear superposition with coefficient c lambda alpha of these eigenvalues. Again, I'm dealing in the Wigner representation. I don't have to, but it's convenient because a phase-based representation in quantum mechanics links much more naturally to a phase-based representation in classical mechanics. So here is my expansion. And in the standard way, I can determine that c lambda alpha is the integral over the initial rho x0 of the function. This should really say rho x0 up on top, the initial value of the density, times this complex conjugate of the Eigen function. And then it looks like this, rho Wigner. I'll just assemble the whole thing together. Looks like an integral over the initial conditions with this combination, which I will discuss shortly. But look at this, the classical mechanics are the same, right? You simply rewrite it as a linear combination of eigenfunctions of the Liouville operator, classical Liouville operator, with eigenvalues of the classical Liouville operator. The coefficients are given by this integral, which is the projection of the initial density onto the eigenfunctions, complex conjugate of the eigenfunctions. And so the evolution becomes this linear combination on the bottom. Looks exactly the same as this, except of course, the eigenfunctions here and eigenvalues here are different than the eigenfunctions here and eigenvalues here. So we all know what the eigenfunctions and eigenvalues are of the quantum Liouville problem. If I can just simplify it instead of writing fancier mathematics, it looks like the ket n bra m I keep losing my cursor, which is why you hear me stopping, is lambda n, n, and m, and the eigenvalues are just the difference. They're the frequencies, which are the difference between the energy eigenvalues divided by h bar. And we can take these and put them into Wigner representation, and that's what I've been writing before. But I suspect that the classical eigenfunctions and eigenvalues are less familiar. And so I'll just call your attention to what they are. The eigenvalues and eigenfunctions of a system which is regular or integrable. An integrable system is a system where n degrees of freedom have n integrals of motion. These are systems which mostly we use when we teach elementary classical mechanics or quantum mechanics. The number of degrees of freedom equals the number of integrals of motion. But in that case, one can define action angle variables. I are the actions, theta are the angles, and the eigenfunctions of the classical Liouville operator for the integrable systems look like this. They look like delta I prime minus I. I is a function, I prime is a number. Well, it's a vector, but it is numerical. And e to the I k theta. Theta are the angles, k is the eigen, dictates the eigenvalue. Lambda is I prime k, k dot omega I. These are the frequencies of the system, and these are the actions of the system. So what this is both stationary, and I see I have a typo here, stationary and non-stationary eigenvalues and eigenfunctions of the classical Liouville operator. They are on a torus. Here's my picture. Here we have a stationary state, eigenstate of the Liouville operator. It's on a torus in phase space with uniform distribution. That would correspond to k equals 0. For k not equal to 0, one gets a whole set of eigenvalues and eigenfunctions, and they look kind of like this, where you have non-uniform distribution on tori. And of course, the situation here we're discussing is for the limiting case of a completely integrable system. There are, at the other extreme, which I'll mention now, chaotic systems, but in between, there are a whole class of systems where there are n degrees of freedom, but less than n integrals of motion. So these are relatively straightforward, relatively simple to understand. This defines the torus. This defines essentially wrapping around on the torus, and this defines the eigenvalue in terms of the frequencies on the torus. But this situation is very different when it comes to eigenfunctions and eigenvalues in chaotic cases. Eigenfunctions and eigenvalues in chaotic cases are actually a mess. So here's what they look like. Rho E lambda is the eigenvalue. E is now defining the energy. You see it's confined to the energy hypersurface, as you might expect from an ergodic system, confined to energy surfaces. Lambda, the eigenvalue, and then tau and eta are two complicated functions which define these chaotic eigenstates in classical mechanics. Tau labels a time to get to a phase space point. So imagine that you start out with a fixed position and it takes you a certain amount of time to get to that position X. That's what this tau is. L, which I wrote this way because PowerPoint makes it difficult to write a nice L, labels the infinitely countable degenerate eigenstates that have an eigenvalue lambda. So the eigenvalue is lambda, but there are an infinite number of states with that lambdas. And eta labels the trajectory. So if you wish to generate this function, for example, you might start at some trajectory, evolve that trajectory in time. That fixes the value of eta. Tau then tells you how much time it took to get to a certain point, and that gives you this function, rho E lambda X. So you want to see how complicated this is. First, note that the infinite degeneracy of the eigenvalue causes a lot of correspondence problems. And second, these are truly complicated states. So I quote here from the paper that we wrote: as one moves off a trajectory, the variables tau and eta must take on all possible values infinitely often, since A, there are an infinite number of chaotic trajectories. B, every chaotic trajectory comes arbitrarily close to every phase space point on every other trajectory, and chaotic trajectories turn arbitrarily close to the original starting point. So these are a mess. But now I just want to go qualitative for a bit. This is the sequence that I showed you before, starting with some initial wave function and ending up with the time evolution of the wave function, quantum mechanics. This is starting out with some classical density, evolving and ending up with this result in classical mechanics. So if you look at this, you learn right away some remarkable and significant qualitative features. The first one is that the idea of complex eigenvalues and eigenfunctions, which we talk about in quantum mechanics, is not quantum mechanics, it's mathematics. So here, for example, these functions, which in quantum mechanics are complex eigenfunctions of the Liouville operator, are also here complex eigenfunctions of the Liouville operator. And in fact, in the harmonic oscillator case, as you might expect, these are actually the same. So you can see in the harmonic oscillator case nodes, and you can see positive and negative character of the eigenfunctions and so on. So when you mention the complex eigenvalues and eigenfunctions, that's not quantum mechanics. That's just Hilbert space mathematics. And similarly, you talk about superpositions. Superpositions are here. This is a superposition of the states. This is a superposition of the states. When you talk about superpositions, again, you're not talking quantum mechanics, you're talking mathematics. And finally, or not finally, but in addition, and one can pick out more, if I look at this thing over here, there's actually time evolving interference between all these states. Here is this, and if you say, looked at this quantity and you looked at taking the average value of some operator, then you would find interference contributions because there are different contributions to your Wigner function, your density, as a function of time, and you look at it and say, oh, I get interference. But it's exactly the same thing here. You get the same kind of interference in classical mechanics. So again, time evolving interference is not quantum mechanics, it's mathematics. So of course you immediately say, well, where do these things differ? And the answer in its simplest sense is that classical mechanics demands that this collective row of xt, I call it a collective row of xt because you see it's built from a superposition. Many of these things can be under, depends on the system, but these are complex functions. They add together, and classical mechanics demands that this thing is a positive everywhere function. Quantum mechanics demands that this row Wigner satisfies the uncertainty principle, the states are of size dictated by h bar, and so on. So you can think of this as, here you have this Hilbert space of functions. In this Hilbert space of functions, classical mechanics picks out ultimately ones that it likes that are positive, and quantum mechanics picks out ones that it likes that satisfies uncertainty and conditions on the size of the states. So what was and this was my idea, but you'll see I couldn't carry it out without Wilkie. My idea was the time evolution looks like this in the quantum, like this in classical. So quote, all I have to do is show that the Wigner representation of the Eigen functions goes in h bar goes to 0 to the Wigner representation of the classical eigenfunctions, and similarly with the eigenvalues, and then I prove correspondence. The problem is always the same. It's essential singularities. So let me just remind you about essential singularities and why this is a miserable problem. So if you look at any of these quantities in quantum mechanics, go back to the eigenfunctions of the Liouville operator written in this simplified way, and and you look, for example, at the Wigner representation, and you can look at, doesn't have to be the Wigner representation, you can see it in all sorts of places. Then right here, you have e to the I p dot b over h bar. And if you're going to use the tool h bar goes to 0 as a way to get to the classical limit, this function is terrible. This function is an essential singularity at h bar equals 0. So let me remind you of what is called Picard's great theorem, which is in every neighborhood of an essential singularity. So here the essential singularity is h bar equals 0. The function, that is this thing, takes on every complex value, except with possibly a single exception, an infinite number of times. So if you approach this limit of h bar goes to 0 from different directions, you will, amazingly enough, pass through every single complex value an infinite number of times. So as I put it here in my less mathematical statement, h bar goes to 0 limit is miserable. So this was the problem that we started to face when we attempted to solve the problem for correspondence in chaotic dynamics. And I want to say that correspondence in the integrable case, we had solved before and it wasn't very difficult, but we established a correspondence program to address both of these in 2 papers. And this is where I'm forced in a way to just sketch the papers. One of them was this one, and you see it's an old paper, but nevertheless, I think this stuff is beautiful, was beautiful, still beautiful, and well worth going back to. So we established it in this paper and in a second paper on correspondence for chaotic Hamiltonian systems. It looks like this. And here is where, again, I have to give credit to Josh Wilkie, because although I had the idea, and although the idea was sound, actually carrying out the mathematics was really a pièce de résistance on his part. I'll try and give you a sketch of what this is about, but what is the essential message is the following. My idea of having correspondence of Liouville eigenvalues and eigenfunctions in the fashion I described here, try and do this, that works for non-chaotic systems. But if you go to chaotic systems, it just doesn't work. Even though in the integral case, you do have to jump over lots of hoops to avoid essential singularities. In the chaotic case, this just doesn't work. So what procedure does work? And the procedure is the following. First of all, you have to recognize that, and this is a long-standing, well-known problem, that t going to infinity, as time going to infinity, where one would see the essence of chaotic behavior, and h bar going to 0, they do not commute. And it's actually easy to see, because imagine that you decided to study a ball, which you're going to throw, and you want to look at the long-time dynamics, and you start out quantum mechanically with this ball, then you have 2 choices. You either can take h bar goes to 0 at the beginning, which means you have a classical ball in your hand, and then go t goes to infinity, or the opposite, which is you treat this ball as a quantum mechanical entity until t infinity, and then you take h bar goes to 0. But if you think about it, what we have generally is a ball in our hand, and we're trying to understand this from the point of view of quantum mechanics. So the way to do it actually is to take h bar goes to 0 first, and then t goes to infinity, and then examine the time propagation carefully. So this was the time evolution. I showed it to you before, but it turns out that it doesn't work. And what happens is you run into enormous problems with essential singularities. But what does work is the following. Go back to the expression for the Wigner. Here it is, and look at these bracketed expressions. This is basically the phase space picture of a spectral projection operator in the Wigner representation. This is the phase space representation of a spectral projection operator in classical mechanics. And what you can show is that this entity goes to this entity in the classical limit. In other words, the eigenvalues don't go to the eigenvalues. They run into tremendous problems with essential singularities. But this way of doing it eliminates the essential singularities, and you're able to actually achieve this result. And part of the reason is because of these degeneracies, which I've sort of not indicated, well, I've sort of buried them in the alpha. Alpha contains all the degeneracies, but I pointed out before that in chaotic classical mechanics, you have infinite degeneracies floating around all the time. So again, there are the details. And I really urge people, if they have the time, to go back and look at this, because it really is impressive how the essential singularities are removed because you're dealing with this product of functions which themselves have essential singularities. But the combination and the example, the combination and the sum eliminates the essential singularities. So that's what I say here, that if you do this and take h bar goes to 0, then they cancel the essential singularities. And the primary result in the classical limit is that the product of stationary quantum Liouville eigenfunctions, stationary, you recall, are lambda equals 0 in the quantum case, k equals 0 in the integrable case. They go to a product of stationary classical Liouville eigenvalues. The product of non-stationary quantum Liouville eigenfunctions goes to a sum of products due to the degeneracy of the classical states. So in my view, this approach is a beautiful approach, and it is driven by the Koopman idea of doing classical mechanics in Hilbert space, and adds here to the classical quantum correspondence problem. As one of the reviewers said of this set of papers that we wrote, the problem of classical quantum correspondence for chaotic systems is extremely challenging, and this is an approach that actually works. Okay, so as an example of underutilized methodologies being utilized, let me try to call your attention to the so-called quantum Nocona theorem. So I'm finished only because it's very complex with the idea of how we can do correspondence using the Hilbert space approach. And I would like to turn to another example of how classical operator methodology sheds light on issues. So here it is. You all know the quantum no-cloning theorem. It says the following, and I've generalized this to densities. It normally applies to propagators applied to wave functions, and it rests upon the linearity of the Schrodinger propagator operating on wave functions. And the question is, can you have a device that clones an arbitrary unknown state? So you have a box, a machine, and you stick in a state, and out pops a copy of that state. So the original state untouched, and a copy of that state is made. But the trick here, the trick to the challenge is that the machine doesn't know what the state is. It just takes in a state and spits out states. So the idea here is like this. You have L row. You have this situation here. You have the state you want to clone, row 1, and a little box into which you're going to put the Liouville operator operating on row 1, row S should give you row 1, row 1. And if it's operating on the box operating on a different state, row 2, it should give you row 2, row 2. And so the linearity of this equation implies the following, that if I take row 1 plus row 2, then it should make L row 1 row S plus L row 2 row S, which is, according to this, row 1 plus row 2 row 2. But if this is a general device, then if I put in row 1 row 2, then it should produce row 1 plus row 2 plus the copy row 1 plus row 2. But that's row 1 plus row 2 plus row 1 row 2 plus row 2 to 1. That is not the same as this. So the linearity of the operator implies that you should get this. The ability of this machine to clone arbitrary functions says you should get this, and they are not equal. That's the general proof that says you cannot build a machine that successfully manages to clone an arbitrary state unless the states are orthogonal. So here, that's actually a generalization, which I'd like to think about some more now that I did this for this talk. But here it says that you will not, this machine won't work unless row 1, row 2 is equal to row 2 and 1 equals to 0. If these are pure states, you get exactly the normal no cloning theorem, which is that you can clone orthogonal states. But you can clone states that are arbitrary, and that's the no cloning theorem. You cannot handle arbitrary states. You can handle orthogonal states, but not arbitrary states. Now, here's the point. The point is nothing I've said here has anything to do with quantum mechanics. It just has to do with the fact that L is a linear operator, and this theorem is exactly the same in classical mechanics. That's what I say here. This is entirely true for classical mechanics. There's no device in classical mechanics that can clone an arbitrary state if you just follow the mathematics of the classical no cloning theorem. The argument is an argument based on the linear character of the operator, which is either classical or quantum. And sometimes you see the statement, quantum mechanics is linear and classical mechanics is nonlinear. That's not true. They're both are similarly linear if you look in the arguments based upon the Liouville operator. So you might ask how you do it, in a Xerox machine and so on. Well, the answer really is that you can measure the state in classical mechanics without worrying about disturbing it. In quantum mechanics, if you try and measure the state and find out what it is, you disturb the state. So you can't touch the state if you're going to copy it. In classical mechanics, you can touch the state. And that's, of course, what you do when you use a Xerox machine. You change the machine to respond to the changed device, the changed state. Or alternatively, you can look at the fact that in classical mechanics, the points the states are points in phase space, and so they're generally orthogonal. But I want to make one amusing point. This argument that takes 1, 2, 3, 4, 5, plus the idea that the classical and quantum operators are both linear. We did this stuff years ago, but didn't publish it because when we were about to publish it, someone wrote a very lengthy proof in Phys Rev Letters called the classical no cloning theorem. And quite frankly, I still don't understand why you need that complicated proof. This is a perfect demonstration that the quantum and classical cloning theorem, no cloning theorem, are exactly the same. So finally, I could try the Bourne Rule, but I don't have time. And the idea here was to show that if you actually think about probabilities in classical mechanics and you rewrite them as Hilbert space structures, then you end up with seeing that the probability is given by the projection onto the state squared, which is exactly the same as the Bourne Rule. In other words, the probability in classical mechanics written in this way is in excellent correspondence to the quantum rule. I said it to one of the, I sent it to Kurt Gottfried, who wrote this nice quantum mechanics book in the old days and a rewrite many years thereafter. I said to him that, if Bourne would have known this Hilbert space structure of classical mechanics, he would have derived this form by analogy. Instead of, if you look at the Bourne paper, it's quite amusing because the footnote corrects in what's in the paper. The paper says that the absolute value of psi of x dx is the probability of finding the system between x and x plus dx. And a little footnote in the bottom says it's not psi of x dx, it's absolute value squared of psi of x dx. That would have been clear from correspondence if Hilbert Space classical mechanics was available before he postulated this rule. So in any case, this is what I wanted to tell you. The details are really in these papers. I do want to thank Josh Wilkie, who did this as a graduate student at the University of Toronto. After he had completed his PhD thesis work, he said to me, I'd like to stay another year. Is there anything I can do? So I gave him this hardest problem I can imagine, which was this one, and he really managed to solve it. And the second, thank Zhanbing Gong, who did the work on the no cloning and the Bourne Rule. He's now at the physics department of the National University of Singapore. And I thank the Natural Sciences and Engineering Research Council of the University of Toronto for support. And I thank you for your attention.
Thank you very much. Are there any questions for Paul?
I have a question.
Yes, please go ahead.
Okay. Professor, you said that the superposition rule is just mathematics and it's not quantum mechanics, and it also exists in the classical Hilbert space representation. Now, physically, we know that classical mechanics doesn't go well with superposition rule. We don't have it physically. How do I understand it in the framework of Hilbert space representation? Unless I use the Sudarshan perspective and take it to a two-dimensional quantum system, that's another thing, but that's it.
No, the way to understand it is when you look, let me go back to that equation. I have to share my screen again. Try to show. So the way to understand it is to see how the states are built. In other words, when you look at a quantum mechanical entity, let's say the evolution of the wave function, or the density matrix in this case, then you would simply see this evolution of this thing, and only decomposing it in this way tells you that it's built of a superposition. Now, if you want to make a superposition as the initial state, so you'd start out by building a superposition to start. But the point is, this is if I was a numerical person, I might study this thing here without ever studying this thing here. But the fact is that I can make initial superpositions here, and I can evolve them in time in this way. I can make initial superpositions here and evolve them in this way, but unless this is positive everywhere, it's not a classically allowed entity. That's the major difference. So it's built out of superpositions, but it requires that and the superpositions are functions which are complex, with complex exponents to the time evolution. But this thing here is what you know as being, has to be positive. Now, if you try to make a superposition of two states here, which is what you would think about over here, for example, you would end up with a row which has got negative characteristics and therefore is disallowed in classical mechanics. So that's the major difference.
Thank you. It was nice.
Robert?
Hi, yeah, thanks. I like your point about considering limits of spectral projections rather than individual eigenfunctions. That's very good. But usually to get nice behavior of spectral projections, you require a spectral gap. And I didn't see the spectral gaps in your presentation.
Yeah, so the spectral gap is treated in this lengthy description. The trick is really in taking the limit to keep an energy width. There is a conceptual problem that I have with this energy width, which is whether this actually corresponds to the decoherence phenomenon. But if you keep an energy width, as you take h bar goes to 0, this problem disappears. The levels get closer and closer together, and one ends up with the correct limit. But I apologize in having to refer you to the mathematical treatment, because in fact, it's a subtle issue. Again, keeping the h bar goes to 0, keeping an energy with epsilon, which smooths out it helps smooth out these singularities.
Okay, thanks.
Carol?
Yeah, so thank you. My question is also on the same track as the previous one. So when passing to the limit in h bar to 0, in the mathematical community, there is something around called semi-classical measures or Wigner measures or relatives of it that are called H measures. This has been around since the 80s. And I was wondering how your limit object is relating to these things.
I must admit that I'm not familiar with, can you describe what you're referring to?
So what is actually done kind of from a very gross perspective is that people take the Wigner function of a square integrable function, and then they integrate it against a very nice regular function.
Right.
And when this function is regular enough, they are able to see a limit point, which is a measure on phase space.
Right.
And
So we
these
don't-
objects are usually called, Wigner measures or H measures, depending on technical set differences.
So what they're doing is they're not dealing directly with the Wigner function, but they're dealing with a smoothed out Wigner function.
Exactly.
We don't do that. This to me always relates to the question of whether you need decoherence in order to successfully get the classical limit. That's a whole area of discussion in the literature. Whether the way, this is Zurich's idea and so on, the way to get to the classical limit is you require decoherence. And I would put it into this category, because by building smooth Wigner functions, the smoothing would come out by measurement. For example, you're measuring over a small width or something like that. And I'm trying to avoid that in this discussion.
Okay, thank you.
Next question, or Aurelia?
Hi, Paul. Nice to see you. Very nice talk.
How are you doing?
So I understand how summing over all the degeneracy helps dealing with this degeneracy, and is better than going to h bar equal to taking the limit. Now, what I'm not sure, maybe it's trivial, but how does it change for chaotic system? How does chaos influence this degeneracy? Because at the beginning you motivated this work looking at, well, the distinction between chaotic quantum and classical systems. So can you say a bit on this?
Yeah, sure. So again, I will try and go back to the slides. The problem is here, right here. If I have these states here, this is a very clearly understood, sorry, I shouldn't consider it clear, well-behaved function. You have on the torus, you have wrapping around the torus, which is what this is, and you have eigenvalues depending upon whether the frequencies are commensurate or they're not commensurate, dictates whether you might have some extra degeneracies in your problem. But the chaotic eigenstates are like this. And as I pointed out here, they have an infinite number of chaotic trajectories. They come arbitrarily close to every phase space point. That would have to be necessary for ergodicity and so on. And there's an infinitely countable set of these states. So I guess you can think about it this way. If you want to build this kind of thing, as I said before, you might have to run trajectories. But if you sit at a point in phase space and you want to get to that point, or you want to get to the immediate neighborhood of that point, because the dynamics is ergodic, because the dynamics is mixing, you will have an infinite number of trajectories that come arbitrarily close to every point. It's that degeneracy which causes the problem and necessitates this sum here.
Yeah,
Sorry?
I see.
Here.
So it's really because the motion is not regular and that you have this infinite trajectory.
Well,
But
it's worse
you have
than not. It's worse than not regular. Every trajectory, neighboring trajectory exponentially diverges from the trajectory that you're looking for. You have all of these conditions that give you whatever hierarchy level of chaoticity. You might have mixing, you have K entropies, a K system, a C system, and so on. But the trick, not the trick, but the problem is infinite degeneracies of an infinite mess. That's the best way to say it.
Yeah, okay. I get it now. Thanks.
Yeah. Mhm.
Very good. Thank you.
Okay. One more question. I see two hands raised, but I think it's Ulf had a question, I think. No. I guess I had maybe one quick question. So is the sort of more complicated expansion one gets in the case of chaotic dynamics sort of really, does it really require actually to have chaotic dynamics? Meaning, can there be non-chaotic systems that will have the same type of expansion, even though, non-integrable, but also non-chaotic systems? So is chaos somehow essential here?
Yeah, the situation, I just lost my microphone. This procedure that I outlined here, and again, I have to quickly go back and share the screen. This procedure that I outlined here works for any system, be it chaotic, this system here, be it chaotic, be it integrable. I will admit, not having looked at the states, at the systems in between, but I presume that it will work for that as well. Now, are there cases where you have infinite degeneracy and the system is not chaotic? Yes, there are such cases. But again, they don't fall. See, you shouldn't think that the integrable eigenstates here are all that simple either, because normally what we deal with things are on energy, with fixed energy, not fixed action. And so you have a whole collection of actions that satisfy the same energy condition. Remember, these are multi-dimensional problems. So you can have extremely complicated regular systems. I know it works for that. I haven't tried anything in between the integrable systems and the chaotic systems, but I see no reason why this procedure of spectral projectors to spectral projectors shouldn't work.
Maybe we can take one last question. If Professor Klein wanted to ask a question.
Yes. Mm-hmm.
Please go ahead.
You were talking about a lot of correspondences between classical mechanics and quantum mechanics. And I would like to point out that this correspondence becomes much stronger if you add a scalar function to the Koopman operator, namely the Lagrange function. Are you aware of that?
No, but are you changing the mechanics? I don't quite understand what this addition is.
No, this addition, this is again a self-adjoint operator. so it's as good as a Koopman operator. I tried to list to put a list of links to my papers on this conference wall, but wasn't successful. And I will try again, and I will succeed someday. So I show you.
Yeah, I would very much like to see it. Also, if I may just ask rather quickly, does anybody have a comment about the classical no cloning theorem, which I also find to be a fascinating issue? Because you'll see over and over, quantum no cloning, et cetera, et cetera.
Yeah. Okay, thank you.
Thank you.
There's another question, Jonathan.
I was just responding to Paul's request about the classical no cloning theorem. Is that so? I'm aware of some work by people like Matt Leifer and Rob Speckens, in the sense that, you know, if you have a distribution, a classical probability distribution, then that's the object you can't clone. So, you know, but that's maybe that they see that as and I agree with them. That's the analog of the quantum no cloning theorem, is the theorem that if I have a probability distribution, you can't clone it.
Right, so here any density rho, which is a probability distribution in classical mechanics, can't be cloned according to this very simple argument. I would love to see what their arguments are, but this seems very simple.
Yeah, I mean, it's almost trivial in the sense that, you know, if the thing I'm trying to clone is a probability distribution, like 50% heads, 50% tails, then if I just give you a coin, you see its heads, but that doesn't tell you what the underlying probability distribution is, so you can't clone it. So in some sense, the classical one, you know, everyone knows it, but maybe it's a way of seeing what the analogy is between the classical one and the quantum.
Let me just make one point. I don't see it as a distribution. I could do it, I could talk about a single point, right? A trajectory starting at time 0, that's a rho, and you can't clone that. So I mean, that is a quote probability distribution in classical mechanics, but it's not some broadened probability like 50% this and 50% that.